Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing on the tube. The YouTube. Testing, testing. Hello, hello. How's it going, Ton Bin? Alright, we're working on YouTube. Just need to check X. How's it going, Isaac Perez? How's it going, Majetti? Alright, I think this should be live shortly here. Okay. Okay. We're working on going, YouTube. Andre? 1 second. Just need to check X. How's it going, Isaac Perez? Alright, now I can see better. I have like a second monitor Majetti? Where I have the chat window open, but sometimes it's so far away that I like can't even like see the text. Alright, I think this should be live shortly here. Can't hear you guys. Can't see you guys asking questions. Okay. Will you touch on the drama around the paper? Yeah, I heard about it. I don't know too much about it. There's an article I found, so I'll touch on that. Isaac. I don't know these people personally, guys. You know, I'm just a guy on the internet. You know, on the drama around the paper. Yeah, I heard about it. I don't know too much about it. There's an article I found, so I'll touch on that. Isaac. I don't know these people personally, guys. We'll touch on it. I'm just a guy on the internet. You know, we live on the drama around the paper. Yeah, I heard about it. I don't know too much about it. There's an article I found, so I'll touch on that. Isaac. I don't know these people personally, guys. We'll touch on it. I'm just a guy on the internet. You know, we live on the drama around the paper. Yeah, I heard about it. I don't know too much about it. There's an article I found, so I'll touch on that. Isaac. I don't know these people personally, guys. We'll touch on it. I'm just a guy on the internet. You know, we live on the drama around the paper. Yeah, I heard about it. I don't know too much about it. There's an article I found. Yeah, there's an echo because I'm touch on that. Isaac. I don't know these people. How about now? Is there an echo now? No echo, right? Yeah, it's because I have an application audio capture. Yeah, I'm... yeah. I have this thing pulled up. The Gemini 2.0 Live. And I'm getting the audio to come out of that. But it's also using my microphone. That's why I was capturing. Let's go on Sarah, Patrick. All right. Let's start today's stream. Today's stream is called Visual Autoregressive Modeling. We're going to be looking over this paper here. Visual Autoregressive Modeling, Scalable Image Generation via Next Scale Prediction. This paper was released, you know, quite a while ago at this point, but that's kind of how it works. By the time you get to the conference, this is the Neural Information and Processing Systems Conference, also called NeurIPS. It actually used to be called NIPS, but NIPS is slang for nipples, and I guess someone decided that was too cringe, and so now it's called NeurIPS. But it's one of the more prestigious machine learning conferences, and obviously they have a Best Paper Award along with a bunch of other awards, and this paper won. So even though it was published a little bit ago, it supposedly is really good, so let's go ahead and read it and see if we figure out what's good about it. So maybe we can start off with the drama. Andre mentioned it, but the author here, this first author, Qiyu Tian, right? So you can obviously you can see here, Qiyu Tian has a Peking University EDU email, right? And you can see that the advisor also has a Peking University email, right? So you basically have a pretty common story here where you have a academic advisor with an academic student, and then if you look at all the people in between, these are all ByteDance emails, right? So the story here is that this guy, Qiyu, had an intern, did an internship at ByteDance, and then published this paper as part of that internship. And here's an article from shine.cn. I'm not like aware of this publication very much, so I don't know whether this is like trustable or not, or whether this is all fake news, but former ByteDance intern wins NeurIP award amid legal battle. So the award-winning paper co-published with Peking University titled Visual Autoregressive Modeling, blah, blah, blah. Tian listed as the first author. The conflict between ByteDance and Tian escalated to a lawsuit after allegations that Tian maliciously disrupted or was poisoning internal model training by altering code, leading to significant resource wastage. Right? So what does that even mean? So obviously when you have these giant training runs that are going on, a lot of the different engineering people have the ability to SSH into these machines and mess with them, right? And you're doing that so that they can go in there, they can see what's going on, they can maybe change some stuff, right? Because you need people to kind of be monitoring these, right? These large distributed training runs, it's not like you just hit play and then you leave and then you come back a month later. It's like something that there's constantly people kind of monitoring it, looking at the loss, looking at all the different metrics for all the different GPUs, making sure it's all working well. So it seems like what happened is that this guy, during his internship, Qiu Tian, had the ability to SSH into the training cluster, and I don't know about this maliciously disrupted, like that probably you're adding intent there, right? I'm guessing since he was an intern, like he probably just went in there and accidentally deleted some stuff or accidentally changed something, and he messed up this training run. But these training runs generally checkpoint constantly, so if something happens, you can always revert to the checkpoint. So the only resource wastage is like the time from the last checkpoint and then whatever engineering time somebody had to come in to fix what he did. So I don't know about this. Tens of millions of dollars. Legal dispute continues, but I don't know. That's about what I know. I don't know this guy personally. I don't know people in ByteDance or at Peking University. So, that's about as much as I know about the drama. But if anybody else has any interesting stuff to add on that, let's get into the actual paper though, right? Because this is a little bit more of a technical YouTube channel. So we're more interested in the technical details, not necessarily the kind of story around it. So VAR, or Visual Autoregressive Modeling, is a new generation paradigm where the autoregressive learning on images as coarse-to-fine next scale prediction or next resolution prediction, right? So autoregressive learning is really what's fundamentally behind language models, right? And the core idea behind autoregressive learning is this self-supervised learning strategy in which you are predicting the next token, right? A simple yet profound approach where you regress the next token, or you choose the next token out of a dictionary or vocabulary of possible tokens given all the previous tokens, right? So here, this top part of this figure here kind of shows you exactly what's happening here. Language has a inherent kind of order and a one-dimensional kind of direction where you kind of progress down the sentence this way. When you're autoregressively predicting the XT token, you're basically using all these tokens here, and the autoregressive refers to that this process kind of repeats, right? As soon as you predict the word sat, you can then predict the word by, you can then predict the word him, right? And then to predict the word him, you're using these tokens here, right? So that's autoregressive. But this paper is doing something a little bit more clever, which is autoregressive, but in this next scale prediction or next resolution prediction, which is a little bit different than next token prediction. Okay, let's keep going. The results for this paper are on ImageNet 256 by 256, which is a little bit of an old benchmark. I think it's appropriate because this is an intern, so it's like an intern project. So, realistically, an intern isn't going to be training on a huge data set and trying to push the boundaries of like reasoning performance. They're going to be limited to some kind of small baseline where they can do a nice little hyperparameter sweep and they can run it on their relatively small budget in terms of compute, right? The intern isn't getting like $10 million worth of compute budget to spend on this project. They're getting some small compute budget. So that seems appropriate. Improving Frichet inception distance FID from 18 to 1, an inception score from 80 to 350 with a 20x faster inference speed. And I'm not a huge fan of Fréchet inception distance and these kind of automated metrics, especially for something a little bit more subjective like image quality. But going from 18 to 1 is pretty ridiculous. And I have here some charts here just to show how ridiculous this really is. I think it's this one. There's a chart here. Here it is. Yeah, but look at this. So here you have DIT, a diffusion transformer. You have some mass GIT, gigagan. So this is like other types of models here. And the FID lower bound is 1.78, right? And this is getting below that. So even though FID is a little bit of a bullshit metric, like this is insane, right? Like getting this low of a score is pretty impressive. So I think that's part of why this paper's getting a lot of attention, is because, you know, that's a pretty crazy score here. I do have one image just to show you guys, give a little bit more intuition about FID. So here you have a figure from a different paper. FID is evaluated for the upper left. Gaussian noise. So you see here, as you add more Gaussian noise to the face, you see here the FID. So it's a distance metric. So the bigger that distance is, the further away that image is, right? So you can see here that the Gaussian blurred face compared to the normal face, when you add a little bit of Gaussian blur, it really doesn't, you know, add that much distance between them. And then at some point, there's this kind of break where adding more Gaussian noise just drastically shoots up the FID, right? But this kind of response level to how much Gaussian noise you're adding and then how much the FID increases, it depends on the type of noise or kind of corruption that you're doing. So you can see here, this is a different type of corruption where you're swirling the image. You know, here you're adding salt and pepper noise. Here you're blocking out different parts of the image. So you can see how FID is not, it's a little bit of a black box metric in that sense. Not black box in that we don't understand it, right? We know exactly how to calculate FID, but black box in that, like, you know, like which one of these corruptions is more natural or acceptable? Like, do we want something that kind of like has this curve response? Do we want something that's more flat? Do we want something that's kind of like this, where it's 0 and then all of a sudden it gets really high? So this is kind of what I mean when I say FID is a little bit bullshit, is that it's a, you know, what does that really mean, right? But either way, getting this low of a score is really impressive. All right. VAR further showcases zero-shot generalization ability in downstream tasks, including image inpainting, outpainting, and editing. So obviously, for any kind of image generation type of task or image modeling task, if you can show that it works in these kind of inpainting, outpainting type of subtasks, that's generally a strong result. VAR has initially emulated the two important properties of LLM, scaling laws and zero-shot generalization. All right. The zero shot there, again, refers to the fact that you're not fine-tuning it for these tasks, right? So this is an in-painting task where you're like taking inside this red square and you're turning it into a corgi, but it's not fine-tuned for that task, right? Normally, you might have to fine-tune a model in order for it to perform this kind of in-painting task, but here it's doing it zero shot, which means you haven't pushed any gradients that are task-specific. It's just doing that straight out of the training that it did just to get to the fully trained model. All right. How's it going, Hupo? Every time I see inference speed, I always wonder how many steps they compare to, because in many papers I've seen it being an amount way higher than what's used in practice. Yeah, I mean, anything like inference speed and training speed, right? Like, it's a much more complicated story than that, right? Because it's compared to what and on what, right? Any type of speed or computational, like 20 times less memory, right? It's what are you actually running it on, right? Because if you're comparing algorithm A and algorithm B on a CPU, you're going to get a different result than if you compare algorithm A and algorithm B on a GPU. And then is it a GPU that's specifically designed for this type of algorithm? Is it multiple GPUs and you're running this in parallel, right? There's so many different types of hardware that inference speed is actually kind of is too broad of a term, right? I feel like you kind of want something a little bit more specific, such as, hey, on this specific hardware for this specific benchmark, we got this much faster inference speed, but just kind of like an umbrella faster inference speed I don't know. Don't read too much into that. Okay. Autoregressive AR, self-supervised learning, predicting the next token. These models utilize a visual tokenizer to discretize continuous images into grids of two-dimensional tokens, which are then flattened into a one-dimensional sequence for autoregressive learning, mirroring the process of sequential language modeling. Okay, so here they're talking about the way that people normally consume images and encode them to then feed them to some kind of LLM and VLM or something like that, right? And the way that this usually works is you take an image, such as this image of the parrot, and you patchify it, right? You turn it into these patches, and you order these patches in a one-dimensional sequence. And you can see that this ordering is done from left to right, top to down, right? So there's this specific scan order that you're using, and the scan order is using effectively the inductive prior of language and text, where whenever we write text, we write it left to right, top to down. So we're reading the images or turning a two-dimensional image into this one-dimensional sequence by using this left to right, top to down. But there's a fundamental problem with that inductive prior, right? Is that it's not really the right inductive prior for an image where you have a little bit more kind of interdependence between that, right? It's like the token 1 and token 4 and token 1 and token 2, there's more of a relationship there than between token 1 and token 3. And the way that people get around this right now is they actually use, for example, rope embeddings, right? So position embeddings, right? So here, we do not use advanced techniques in large language models such as rotary position embeddings, SWIGLU, MLP, or RMS. No, the important one here is rope embeddings, right? If you're using the kind of classic left to right, top to down, raster, scan order for consuming an image and turning it into a one-dimensional sequence so you can feed it into an attention mechanism, you're putting in those rope position embeddings because this isn't the correct way to do it, right? Because this raster scan is kind of putting in a bad inductive prior there, you're forced to put in the position embeddings to remind the neural net that, like, oh, no, this 1 is actually right above this 4, right? So it allows it to use those position embeddings to kind of understand the spatial position of all these different patches. But this paper is going to reformulate the attention and the autoregressive task for images in a way that doesn't require this type of position embedding, right? And it's a very clever little solution. So humans typically perceive or create images in a hierarchical manner. This multi-scale course-defined nature suggests an order for images, right? We define autoregressive learning for images as next scale prediction. The transformer predicts the next higher resolution token map conditioned on all previous ones. Okay, so this is fundamentally what the paper is, right? Is that, hey, rather than taking images and cutting it into these patches and then reading these patches left to right, top to down, and then predicting the next token or the next patch autoregressively, just using the previous patches, we're going to instead think about autoregressively predicting the next scale or the next resolution, right? So you can see here that you start with kind of one token that represents the whole image, and then you're using that to predict kind of the same image, but the entire image, but at a slightly higher scale. And then you're doing the same thing, predict the entire image, but at a slightly higher scale, and then at a slightly higher scale, and then at a slightly higher scale. So rather than the autoregressive modeling happening in this kind of like one-dimensional flattened image sequence space, it's now happening in this course-defined resolution space, right? And as soon as I saw that, I immediately think a convolutional neural net, right? Because this type of like course-defined inductive prior is exactly what is behind a convnet, right? And I have here a little GIF of how a convolution works, right? And in a convolution, which is what's the basic operation behind a convolutional neural network, right? You have this little filter, right, which you're striding across the image. So here is the image, but this could also be a low layer, and this could be a higher layer, right? So you have these hierarchical layers, and what you're really doing is that each neuron in a higher layer kind of has this receptive field or this kind of large area of the lower layer, which it is using to get that number there, right? So there's this kind of hierarchical kind of coarse-to-fine pattern that you're baking into the convnet there, where you're saying, okay, this little neuron here is kind of aggregating information from this slightly larger area or like spatial volume of the previous layer, and that keeps going all the way down. And you can actually trace that even further back, right? Because here they say, okay, the reasoning for us choosing this kind of multi-scale coarse-to-fine comes, we're reasoning from first principles to get to this inductive prior, right? We're basically saying humans do this, and that's why we're going to try to do this. And that's exactly how convnets happen, right? The way that we got to these convnets like this, right? Where is it? Right here. The way that convnets were originally designed was by looking at the visual system, right? So I'm not a neuroscientist, so I don't know exactly what all of these symbols mean, but the way that your vision system works, right, is that you have images, which you can kind of think of like a pinhole camera model where the image is going in, it's going in through your iris, and then it's basically being projected onto these cells in the retina. Those send a signal all the way to the back of your head. So actually the way that the image moves in your brain is it goes in through your eye, and then it goes all the way to the back of the head. And then there's these pyramidal neurons, right? So basically the neurons in your visual cortex are arranged in these kind of layers, right? Where you have V1, V2, V3. And way back in the day, people went into the neurons of cats. So they actually, I guess, had to kill cats and then cut them open and then cut open their brains and then slice their brains into these little slides. And then they look at those slides and then they see, oh, hey, look at this. The neurons in this V2, each of these little neurons in the V2 is kind of connected to a little patch of neurons in V1. And then the neurons in V1 are kind of connected to this patch of neurons in I guess, whatever LGN is, right? And people realize that there's this kind of hierarchy of resolutions that are happening inside your brain that allow you to build effectively a feature or a kind of semantic representation of the image, right? So the fact that your brain has these kind of layers that have this kind of coarse-to-fine kind of spatial hierarchy, that is the reason that people came up with convnets, and that's basically the same reason that this guy here, Qiu Tian, came up with this idea of next scale or next resolution autoregressive prediction. So that's basically the paper, guys. But maybe we take a step here to think about, why did this paper win best paper, right? And there's a lot of different dimensions in which a paper can be good, right? So a paper can be good because the results are good. A paper can be good because it's really well written. A paper can be good because the idea is very good, right? There's a lot of different things there that can be good or bad. And this paper is really good on all of them, right? So this paper, one, the results are really good, very clean results, right? Like super good FID on this very, very well-established benchmark. Okay. The paper's also pretty well written. I would recommend it if you just want to read a paper kind of front to back. Like, it actually is pretty well written. I think that the way that a lot of these things are explained are actually very clean, you know? So even in terms of just like thinking of a paper as kind of like an educational piece, where it's like, how can I teach people the basic concepts that are required to understand this concept? I think it actually does a good job at that as well. But then also the idea itself is very pleasing, right? The idea of like, hey, here's a very simple concept which comes from a very simple kind of base assumption, and the concept works, right? So those type of papers like the residual connections or skip connections, that was also a similar kind of like something where it was like a very simple concept, but then you apply it and it works very well, right? So like if you really want to win these best paper awards, you're better off playing this lottery of like, let me find something that's kind of like a very simple little concept and then see if it works well. And if it works well, then write that paper very well, and you might actually get this best paper. Sounds like something that would easily expand into the temporal dimension. Yeah, you could do the same thing, right? So the same way that you can have this hierarchy of kind of receptive fields in two-dimensional space, right, like the two-dimensional image space, you could have the same thing in a three-dimensional space, right? So this same exact autoregressive modeling next scale resolution, we're just going to call it VAR. This VAR isn't restricted to two-dimensional space like this, right? And even in three-dimensional encoders and three-dimensional, like if you're looking at something like something that convolves in a three-dimensional space, you're still kind of using this type of bullshit, right? So we've read some of these three-dimensional papers. Maybe you're generating objects, or maybe you're creating some kind of Gaussian. Gaussian splats work a little bit differently, but usually you'll see this exact same kind of raster scan prior, which we know is kind of shit, and we have this intuitive feeling that this is pretty garbage, right? Like, we don't like this kind of raster scan pattern, and we have to hack it with these rope embeddings to even get it to do anything. But in 3D, this also works. In the time dimension, this also works, right? You can imagine a time version of this, and you can even dimension a four-dimensional version of this, which is a three-dimensional space with a one dimension of time, right? So there's a lot of ways to take this idea and apply it to a bunch of different things, which is also why it won the best paper. Okay. VAR directly leverages the GPT-2 transformer architecture. VAR surpasses the diffusion transformer, the foundation of leading diffusion systems like Stable Diffusion 3.0 and Sora, right? So they're not even trying to really juice the shit out of this ImageNet 256 by 256 benchmark, right? They're actually keeping a lot of these tricks off, right? So it's capable of getting this ridiculously low FID score despite not actually using the latest and greatest fancy tricks, right? So they're using a GPT-2 architecture. They're not using some of these more advanced activation functions like the swig-glue. They're not using RMS normalization, right? So there's even more juice that you could squeeze out of this. But even without that, they're showing really good performance. And because a lot of our kind of state-of-the-art systems like Stable Diffusion 3 and Sora and all these other Hunyuan and Hailuo, all these other video generation models, they're still using the DIT. So this is beating that. So you can bet that there's people at all the frontier labs that are exploring training something more like this VAR as opposed to this kind of scan order with embeddings that we've been doing up until now, I guess. Okay, we're going to skip a little bit of this related work here, and we're going to go straight into the method. Let me drink a little bit of water before this. Should we use objects instead of a patch as a token level for images? Words are semantic, but patches are not. So objects being semantic could mimic word tokens. I think it's less to do with like the idea of a patch, right? Because this patch, what's really happening is that patch is being embedded into a vector, right? So in this paper, there's a VQ VAE that's effectively taking this little patch, turning it into some kind of vector, and then really what the sticking point here is the raster scan. It's more so the fact that you're kind of feeding these in left to right, top to down. That's the part that's kind of shitty, right? That's the part that this paper is improving on. But in terms of actually encoding every single patch, like, this paper doesn't propose anything new in that. In fact, it's just literally using a VQVAE. So the VQVAE is using a vanilla VQVAE architecture in order to tokenize. So the image is already tokenized. It's just how are you taking those tokens and feeding them into the attention mechanism, and how do those attention mechanisms, as you go up the scale of the layers, relate to each other, right? So this isn't even a big VQVAE either, right? We use a shared codebook for all scales with V equals 4096. So the vocabulary size, right? Each of these little tokens, image tokens, there's only 4,000 possible values for those, right? So like, whenever you're predicting the next token, in this case the next scale token, or in this case the next patch token, right? Each autoregressive prediction, you're picking one out of these 4,000, right? So it's like a 4,000 classification problem. You're basically saying, okay, out of these 4,000 next possible codes, which one is it? This one, okay. Let's autoregressively predict the next one, and the next one, and the next one, and the next one, and so on. So let's get into this. Preliminary. Autoregressive modeling via next token prediction. This is a nice little summary of what autoregressive modeling is, and basically LLMs 101. You have a sequence of discrete tokens where each token is coming from a vocabulary V of all possible tokens, right? Vocabulary of size V. And for language models, this is on the order of like 100,000 now, right? But for this tiny ImageNet, we're in the order of like 10,000, right? So like, I'm thinking like order of magnitude, right? So like you got tens, you got hundreds, you got thousands, 10,000s, 100,000s. In language models, we're at the order of kind of 100,000 for the vocabulary sizes. For something like this with ImageNet, little tiny neural net, 4,000. But that just goes to show you how much room there is to grow, right? Imagine a VQVAE kind of image encoding with 1 million possible tokens, right? A vocabulary size of 1 million or something like that, right? Which might not be that far away. All right. You have some current token X of t, and then you have this unidirectional token dependency assumption. What that really means is that when you're autoregressively predicting token X of t, you see this thing right here, you're only using the tokens x1 all the way to xt minus 1, right? So there's this kind of assumed direction, this assumed sequence, which is a very good inductive prior for language, but it's not a good inductive prior for images. Then you have an autoregressive model P of theta here. Theta is the parameters, right, that parameterize the model. P of theta is the model, and it really just gives you X of t given all previous X's. This is known as next token prediction. Tokenization. Images are inherently 2D continuous signals, so we tokenize the image into several discrete tokens and define a 1D order of tokens for unidirectional modeling. So your discrete tokens come from this vocabulary of possible tokens, and your tokens are now not in a sequence, right, but they're in a kind of like a two-dimensional map, right? So you now have this H by W of tokens, right? So you've turned your image, which is H by W of pixels, and now you've turned it into H by W of tokens. And you're doing this using a VQVAE, and we're going to show this VQVAE in pieces here, but I think first let's go over the equations for it, and then we'll go into the actual image which describes it. So IM denotes the raw image. You see that? You're feeding your image into this E, which is the encoder. The encoder turns that into some features. Then you can take those features, put them into this quantizer. That's going to turn it into effectively the tokens, right? It's going to pick these vectors given the features, and then those vectors are defined in an explicit, discrete code book. And the way that you're picking the code or the actual specific vector given a feature vector, which is continuous, is you use this Euclidean L2. So you see you're basically looking up the distance and saying the one that is the closest to the feature vector, right? And then once you have that discrete tokens now, you can feed that into the discriminator, or not the discriminator, the decoder, sorry, and the decoder will turn it back into an image. All right, so I think I'm getting a little bit too deep. Let's explain this. And here is a nice little, let's do this one. Yeah, so I fed this image. Now that ChatGPT 01 Pro has image explanation, right, you can literally give it this image, explain every part of this image, and it's actually pretty good. You know, it actually gave a very nice little explanation of all the different parts. It really understood all the different things. This is a little bit cheating because this is a very popular figure from a very popular paper, so I feel like it makes sense that it has a very good understanding of this image because there's probably a bunch of different blog posts and YouTube videos and articles where people describe this. So it's definitely seen this in the training data, but I was still relatively impressed with the breakdown. So let's go into this because I think it's important to understand what a VQVAE is in order for us to understand the VAR paper. So you first start with the image. The image is going through this CNN, this convnet. That convnet is this thing here, right? So let's look at this. This encoder here, this E encoder. Let's zoom in a little bit, right? This encoder E is this CNN, right? And once that encoder is done encoding the image, you're going to end up with this feature map version of the image, right? And it's still two-dimensional, but now it has some depth d, right? So you changed it from being some height by width in pixel space and then 3 channels into now this d, which is the dimension of each feature vector, which corresponds to this spatial region in the image, right? There's some receptive field that this feature vector has, and then this feature vector, and then this feature vector, and then this feature vector. And each of these, the encoder produces a latent code, which we call ZEX, this thing here, right? This offers a high-dimensional tensor, reflecting some compressed high-level features. ZEX is not discrete, but a continuous vector, right? So each one of these green squares is going to be this continuous vector. Like, you can think of it like this long, skinny rectangle, right? And that long, skinny rectangle is kind of representing what is in kind of this part of the image, right? And this part of the image for this one. But now you have this VQVAE. The heart of the VQVAE is a discrete codebook, right? So you have this codebook which has a discrete, or just a specific set, a specific amount of these vectors here, E1, E2, E3, EK, right? And what you're going to try to do is you're going to try to say, okay, for each of these continuous vectors that I'm getting out of my encoder, what is the nearest vector in the codebook? And that's kind of what they're showing here. So each of these vectors, E1, E2, E3, is one of these purple dots, right? And then here, this ZEX is the specific little green dot that is here, or maybe the one that's here, maybe the one that's here, maybe the one that's here. And what you're saying is, okay, which one is it the closest to? Okay, because this is continuous, this green dot can be anywhere, but these purple dots are kind of a little bit, they're specific and fixed, right? So you're saying, which one is it closer to? It's closest to this one? Okay, so rather than this continuous green feature vector that here, I'm going to say E2. And then here I'm going to say E3, and then E1. So you can see how we're replacing each of these ZEXs, which is continuous, with the corresponding index of the vector in this codebook, right? So you're kind of discretizing it. Okay. You can think of the codebook as a dictionary of representative latent vectors. Instead of working with a continuous ZEX directly, the model quantizes it by choosing the closest embedding vector from the codebook. Okay. Once you do that, you can then take that ZQX and feed it back through a decoder, which is very similar to the encoder, right? The encoder takes the image in pixel space, turns it into this feature space. The decoder takes the feature space, turns it back into the pixel space. But the decoder isn't working with these vectors here. It's working with the closest codebook vectors, right? So you've replaced all the vectors here with the closest ones, and now you're feeding it back through here. So this is a little bit different than this. So that means that this image is going to be a little bit different from this image. And then what you can do is say, okay, well, I can compare this image and this image because these two should be the same image, right? Or at least I want those to be as similar as possible. So, right, you're looking up the closest vector for your Q inside your codebook. Then you take that final image. This is the image that was inputted into the encoder. This is the image that's outputted by the decoder, right? Here's just the distance between these in pixel space. Here you have the distance between the vectors, or the kind of the feature representations of those images. And then you have also perceptual losses such as LPIPs and a discriminator loss. But really what you're doing here, this loss, this multi-component loss here, is really just this image should look the same as this image, right? Like that's fundamentally the at a high level what you're trying to do is you're trying to make this image and this image the same, and this is the loss that allows you to push gradients all the way through that. And whenever you're pushing gradients, right, you're not just pushing gradients into this CNN and this CNN here, you're also changing this codebook, right? So these little vectors here that you have kind of hard-coded, these tokens, right, the gradients ever so slightly adjust those so that over time, as you continue to feed more and more and more and more images into this VQVAE and start pushing more and more and more gradients, these discrete kind of effectively tokens, you can think of it that way, start covering all of the embedding space, right? So initially your codebook is just kind of a bunch of weird, shitty vectors that are maybe evenly spaced. And then over time, they start kind of like moving around, and you're trying not to get all of them to collapse to the same place. You want them to kind of like evenly distribute all around this embedding space so that anytime you put any random image and you put it through the encoder and then try to find the nearest token to that specific token, there's bound to be one of these little code vectors right there. And you can just say, okay, well, I'm just going to use this little code vector here rather than the continuous one that I got from my encoder. Does that make sense? Did I lose people? All right. And that's the autoencoder, right? So when we describe an autoencoder, we're really describing multiple parts here, right? We're describing the encoder, the decoder, and this quantizer here with the codebook. All right. So now that you've trained this, and they don't train this themselves. I think they use a pre-trained version of it. In fact, they mention it in the next steps. Ablation study right here. We expect advancing the VQVA tokenizer as another promising way to enhance autoregressive generation models. So they didn't even mess with the VQVAE, right? The VQVAE, this is basically ancient at this point, right? But it still works very well. So this paper isn't trying to solve all of the problems, right? It's just literally showing you one little trick or kind of way of reframing the problem that works well, but they don't mess with the kind of tokenizer, right? They don't mess with the transformer architecture itself, right? They're still using the same kind of GPT-2 standard transformer architecture. So really the only thing that they're changing is this fundamental inductive prior of like, are we moving left to right, top to down, or are we doing this kind of multi-scale kind of, I think of it like a convnet, right? The way I see this is like a convnet for the attention map. It's like an attention map convnet. That's like the way that my brain wants to describe this. So that's the VQVAE. That's how they're turning these, the image into a grid of tokens, right? Where each one of those little tokens inside this H by W grid is coming from this vocabulary of 4,000 arranged in this two-dimensional grid. But, and then this is the fundamental part of the paper, unlike natural languages sentences with an inherent left-to-right ordering, the order of image tokens must be explicitly defined for unidirectional autoregressive learning. So previous autoregressive methods flatten the two-dimensional grid using a row major raster scan, a spiral, or a Z-curve order. Here's an example of what they're talking about here, right? So this is the row scan, which is probably the most popular one. Pretty much everyone uses this, right? Just left to right, top to down. But we've also seen a bunch of different variants of this, right? I remember reading a Mamba paper where people did multiple scan orders, right? So they did left to right, top to down, then they did bottom to up, right to left, and they did both of them separately and then combined the outputs, right? There's even fancier kind of scan orders like Z order curve where you make a little Z and then more Z and then Z, like you got here Hilbert curve, right? So there's a bunch of different ways you could create these orderings, right? But none of these are good, right? Like fundamentally the problem here is that no matter what fancy raster ordering you do, it's still not the right type of prior for images, right? Because image feature maps have bidirectional correlation. This contradicts the unidirectional dependency assumption of autoregressive models. The nature of image autoregressive modeling restricts their generalizability in tasks requiring bidirectional reasoning. E.g., it cannot predict the top part of an image given the bottom part. What they're saying there is that whenever you're using this raster scan like this, right, every single time in training, this transformer has always been fed the top left of the image first, and it's trying to predict basically down towards the bottom right. So unless you're like doing up-down flipping, left-right flipping, it's never predicting the top of the image given the bottom of the image, right? Which is where this kind of prior can start creeping in stuff that you don't want, right? Flattening disrupts the spatial locality inherent in image feature maps. Token Qij and its immediate four neighbors are closely correlated, but this spatial relationship is compromised in the linear sequence X, which is where unidirectional constraints diminish these correlations, right? And the trick that we've come up with to fix that has always been these position embeddings. But if we can just come up with a better inductive bias, we don't need these position embeddings, and that's what this paper is, right? It's a better bias. It's a better prior, not inductive prior, I think is the right term. Okay. So let's understand this multi-scale a little bit better, right? Because it's still a little bit like fuzzy. Like what the fuck does it mean by multi-scale? Like what exactly is going on here? VAR involves two separate training stages. Stage 1, a multi-scale VQ autoencoder encodes an image into K token maps all the way up to RK. Multi-scale quantization. So you have your VAE. It encodes the image into this tokens, effectively, right? So basically this process here, right? You're taking this image, which is in pixel space. You're turning it into continuous vectors. So each of these green squares, right, represents is a multi-dimensional continuous vector that represents the semantic information in this part of the image, right? Where the receptive field of the convolutional neural network tells you kind of how much of the spatial 2D image is actually being encoded in this part, right? And the way convolutional neural network receptive fields work, you're not getting the entire image, right? So you're really like this 155, that's only based on kind of this top corner-ish. It's really not using any of the stuff at the bottom. So the same thing is kind of happening with this VQVAE, right? Where this little green square here is more so representing what's in this top part than the bottom part, right? But then you're feeding it into this quantization process, which then picks the closest, effectively, token out of this vocabulary of possible tokens, and then that's what these token maps are, right? So you have token maps of different resolution, but each one of these little squares in the token map is one of these vectors in the codebook, right? One of these words or words in the dictionary, if you want to use that vocabulary instead. Okay, so that's stage 1. And you're decoding, and then you basically are taking this image and taking this image and saying, okay, this image should be the same as this image, and then we just keep pushing gradient, and then that's how we train this multi-scale VQVAE, right? So stage 1 is just your classic VQVAE, and like, why is this popular? The reason this is popular is because this is entirely self-supervised, right? You don't need to provide any kind of label or learning signal for this image. The label and the learning signal for this image is literally the image itself, right? So VQVAE is very easy to train because you don't need to label, you don't need to have bounding boxes, you don't need to have any of this bullshit, you don't need to have captions or anything like that. You're literally just, the image itself is the signal, right? So the image itself is what you use in your losses, right? These losses here, there's no target here, there's no whatever the fuck, it's like literally the image and then the image that comes out of the decoder. So that's why a VQVAE is very popular, because you can just train it on 10 million images as is, you know? Okay. Then we get to stage 2, training the VAR transformer on tokens. Okay, so now we've trained this VQVAE, which can take our image and turn it into this, effectively, they call it a feature, image feature map F, right? But that's just a fancy way of saying we've turned this image into tokens that represent the different parts of the image, okay? And now this is where there's a little bit of like 5D thinking that you have to think here, right? So previously, right, we're used to this, okay, you have this 2-dimensional image feature map and you raster through it, and now it becomes a 1-dimensional sequence. And once it's a 1-dimensional sequence, then we can very easily fit this into our previous mental model of like next token prediction and autoregressively predicting the next token, because that's all based on these 1-dimensional sequences. But how do you formulate this like multiple hierarchy? Like, what the fuck does that mean? Are you feeding this entire thing into the thing? Like, what is going on? Because aren't these different dimensions, right? Like, so you have to kind of like, I call it 5D thinking, but it's like being able to visualize tensors of different dimensions in your head, and then how they kind of like morph and multiply against each other, right? So like, it's pretty easy to think of matrix multiplication in your head, right? Think about two-dimensional matrices. And when I think about matrix multiplication in my head, I'm like, I can see almost like a little GIF of like the rows going and then the columns going and then that producing each square. So like, that's kind of what I'm thinking about. And there's a similar kind of like mental visualization you need to do here of like, okay, how is that being fed into this autoregressive transformer, which is a 1D thing, right? Or a set to set, you know, people that are fancy like to say attention is set to set, right? And the sequence really only just comes from these position embeddings, but the attention mechanism itself doesn't actually have anything that forces it to be a one-dimensional sequence, right? Because it's really just a set of things and then another set of things. The ordering doesn't matter until you put the position embeddings in there. And this one doesn't have position embeddings, so the ordering doesn't actually matter. Okay. It takes S. This first token here is actually a class token. I think they mention it down here. Where is it? Okay. I don't know where they mention it, but that first token is a class token, right? So it's like a token that doesn't represent a specific spatial part of the image, but kind of like the entire image. Okay. Oh, start token, sorry. Start token with conditional information. So you have your start token, then you have R1, R2, all the way to RK minus 1. You see here R1, R2, R3. So basically the subscript here on the R represents the hierarchy within this multi-resolution map. Is used as input to predict R1 all the way to RK. So here's the autoregressive part, right? Where RK is basically only seeing up until RK minus 1, right? So you're only using the stuff before, except rather than the stuff before being kind of what's before you in like a sequence ordering, it's what's before you in this kind of hierarchy of scales. Okay. The attention mask is used, ensuring that each RK can only attend to R less than or equal to K, right? So an attention mask, pretty standard, but for example, when you're here and you're trying to predict in a classic raster scan kind of paradigm, right? When you're trying to predict this token number 5, you have an attention mask that prevents you from paying attention to tokens number 6, 7, and 8, and 9, right? You're only paying attention to tokens 4, 3, 2, and 1, which is why you have this fundamental problem here of cannot predict the top part given the bottom part, because it's literally, there's a mask there preventing it from using the bottom part of the image. Okay. Each RK can only attend to R less than or equal to K. Here's a blockwise causal mask. Reformulation. The autoregressive unit is an entire token map rather than a single token. We start by quantizing the feature map, H by W by C. So this C here, right, is the D here, right? So the dimensionality of this here, or the dimensionality of these, right? So each of these little tokens or words in your dictionary or codes in your code book, right? This is some vector, this has some dimensionality D, right? That's what's going on here, right? So you have an image map of height H by W and then some dimensionality C there into K multi-scale token maps, each at an increasingly higher resolution HK by WK, culminating in RK, which matches the original feature map's resolution H by W. All right, so this is where you start having hyperparameters, right? Because pretty much in any kind of architecture design paper, you're going to introduce these hyperparameters. And a hyperparameter is something like this, right? Like, for example, this lambda p here, right? This is a hyperparameter which determines how important is this perceptual loss over here compared to this the distance between the feature vectors in embedding space. So some human has to decide what the value for this lambda p is, right? Some human has to decide what this value for this lambda g is. And similarly, some human has to decide what these resolutions are, right? So there is a little bit of hyperparameter magic there where it's like, okay, well, what are we talking about here? Is this image, if this is a 250 by 250 image, is this like a 128 by 128, or is this a 200 by 200? And then you have so there's some design there, much like a convnet, where in a convnet you have to decide on these little hyperparameters like the stride and the size of this little kernel or the feature here, right? Like there's how many layers, right? There's all these different hyperparameters in a convnet, and similarly there's all these little hyperparameters here as well, right? And there's more so like the different resolutions that you're doing these feature maps at, these multi-scale token maps. All right, here's the same autoregressive prediction, right? You're predicting RK based on up until RK minus 1. Are we using the same VQ-VAE for all the resolutions? Yeah, so the way that they're getting the different resolutions is they're interpolating. So I think they actually say it down here. Conditional RK, let me see, Control F. interpolate. Yeah. Here. Yeah, here we go. So this is how they get the multi-scale VQVAE, right? So you can see here they're interpolating. So RK, which is the resolution map at resolution K, I guess, there's K number of these hierarchical resolutions. In order to get the smaller ones from the bigger ones, you interpolate. You see that? So basically what you're doing is you're making this large map, and then you're interpolating these other maps. Does that make sense? Doing as few new things as possible makes it more clear what's causing improvements. Yeah, I mean, that, like I said, this paper is filled with little things that make for a good paper, right? If you have a paper where you get good results, but you use like 700 different little tricks, you know, that's not as good of a paper, because it's like, it's really, you're just kind of using all these different tricks. It's not very satisfying because it's like the accumulation of a bunch of little different tricks in order to get the good result. But here, they're getting a good result with like removing things, right? They're like removing tricks, and they have a new kind of simpler prior, and it works better. So yeah, the fact that this is relatively simple and they still get a pretty good result is part of what makes this the best paper award winner, right? Thinking similarities to the protein model, which the encoder is rotation and symmetry agnostic by geometric invariance. Yeah, pretty much. Like, I think you can apply this, and maybe not this specifically, but this type of thinking, where when I look at we've reviewed some biology papers, right, where they're doing these proteins and these amino acids, and like there's a similar kind of situation where everyone wants to use a transformer, which means that everyone needs to figure out a way to take their data and put it into this one-dimensional sequence, right? So whether it's a three-dimensional object, whether it's a two-dimensional image, whether it's some kind of protein or some kind of graph, you know, some kind of weird data type of modality, everyone figured out their own special magic way of converting that data into a one-dimensional sequence, right? And unfortunately, all of those little independent magic ways of converting that data, whether it's a protein or a image, into a one-dimensional sequence so you can feed it into a transformer, pretty much all of them are a little bit wrong intuitively, right? They're all kind of a little sketchy, kind of like this one here, right? We were just left to right, top to down, right? It just doesn't feel correct. So for something like a protein or an amino acid, maybe amino acid sequence is a little bit less sketchy because it is a one-dimensional sequence, but for sure there are other areas in science where people are flattening things into 1D sequences in order to feed it into an attention mechanism, and that flattening process could be improved. So there's probably other papers that could be written where it's something like this, where you're kind of, it's probably not going to be the same exact kind of multi-scale thing, but something similar to that, where like, hey, let's go back to the building blocks. What is a better way, a better prior that we could use, rather than just kind of this naive flattening that we're doing for this specific data modality? And for images, the prior is very obviously multi-scale hierarchies, right? Because as we were saying at the beginning of the stream, the multi-scale hierarchy, that intuition literally comes from the way that our brain and the neurons in our brain work. And that intuition worked very well for ConvNets, so it makes sense to use that same intuition to think about a better way of creating this autoregressive task, or formulating this autoregressive task for something like an image. Okay. Each autoregressive unit, so each of these maps, you have HK by WK, right? And at each resolution, you're going to have to kind of pick what this K is, right? So the HK and WK for the very first one is 1 by 1, right? But then as you go to the second one, it might be 2 by 2, and then so on. You have to kind of pick what those are. And then here's the magic that adds the 20x inference speed, right? So this 20x faster inference speed, where the fuck did they get that from? Well, here it is. All distributions over the HK times cross WK tokens and RK will be generated in parallel, conditioned on RK's prefix and associated with the K position embedding map. So during inference, KV caching can be used. No map is needed. Blockwise causal attention mask. But, okay, so this in parallel is kind of part of what makes this magic work, is that the same way that ConvNets, right, the original ImageNet ConvNet, like why did ConvNets perform so well on ImageNet? It's because you were able to take this and put it on a GPU and do it in parallel, right? So on a GPU, you could say, hey, I don't need to be doing these independently like this. I can do all of these in parallel because this one doesn't depend on this one, right? This one here doesn't depend on that one. I can just do them in parallel, calculate that all in parallel, and that means that I can feed millions and millions of images through this ConvNet on a GPU and then end up in a good place, right? So there's this kind of weird relationship in the universe where spatial hierarchies of multi-resolution are inherently something that you can parallelize on a GPU. So the same way that ConvNets ended up being magic because you could parallelize them on a GPU, this type of autoregressive formulation where you're doing this multi-scale hierarchy, right, the same underlying base inductive prior also allows you to do the same thing and calculate these in parallel, which you can't do here, right? Because the problem with this type of flattening like this is that you can't do number 9 until you've done number 8, and you can't do number 8 until you've done number 7, and you can't do number 6 until you've done number 5, and you can't do number 5. So you see what I'm saying? You're waiting. You can't do that on GPU because you're sitting there waiting for that number 9 before you can do number 10, right? So it's like the one-dimensional flattening forces you into this kind of autoregressive prison where you have to wait for the previous thing to finish to get the next one. But the way that this works, right, because you're doing this multi-resolution, you can do the entire resolution at the same time. Or each layer can be done at the same time, the same way that you could do it with a ConvNet, where you can basically do this entire layer at the same time because each part of that is not dependent on all the other ones. I think that's kind of the core thing that we need to think about there. Okay. Let's go back here. Spatial locality is preserved as there is no flattening operation. Complexity for generating an image with n by n latents is significantly reduced to O(n) to the fourth, and this arises from parallel token generation in each RK, right? So each RK, each of these hierarchical resolutions, you can do it all in parallel because it's only using the previous ones that you've already done, right? It's not dependent on this kind of like 1D sequence where you have to wait for the one previously to work to get the one that this one. Tokenization. We develop a new multi-scale quantization autoencoder to encode an image to K multi-scale discrete token maps. Multi-scale quantization autoencoder. So the quantization autoencoder, this thing, you have multiple scales. So you have multi-scale discrete token maps. But the shared codebook Z is utilized across all scales, which is actually kind of trippy to think about. Each of RK's tokens belong to the same vocabulary V, which is really weird to think about, right? Where if you think about this codebook here in a classic VQVAE that only has one resolution, right? Each one of these tokens is representing a concept which has the same kind of receptive field, right? So this token number 1 maybe represents ears, and this token number 2 maybe represents like the nose, and this token number 3 represents eyes, right? So like each of these tokens has the same kind of like receptive field, and thus to me it's like they're almost like words in this dictionary that are representing different things, but they're all representing different things at the same level of like resolution hierarchy. But the weird thing here is that they have multi-scale quantization, right? So this is happening at multiple scales, right? And the vocabulary is shared, which is really weird, right? Because at a very high scale, right? So whenever you have this like this here, and it's like 10 tokens by 10 tokens, each one of these little tokens is like that token probably represents something very micro, right? Like the texture of the beak of the parrot, right? But that specific word in that vocabulary that represents the texture of the beak of the parrot is in the same vocabulary as a word that represents the entire concept of a parrot, right? So there's something weird about that, but maybe that's where some of this magic works, right? Is that you have this shared codebook across multiple scales. So the different tokens or the different words inside this dictionary here, this vocabulary, are representing concepts at different hierarchical kind of resolution scales. And somehow that makes it work better, you know? Which is maybe like whenever you think of like a skip connection in a convnet, like is that kind of a similar thing that's going on, right? Like this idea of like being able to pass concepts that are existing at a lower layer into like higher layers. Is that kind of analogous to this a little bit? Each RK token belongs to the same vocabulary. We upscale ZK to HK, WK, where we use K for extra convolutional layers, or we use K extra convolution layers. So that's how they're upscaling. All right, here's your algorithm 1, algorithm 2. You can see the standard stuff here is your interpolations. You have your K steps. This is your encoder. This is your basically decoder. So your decoder takes some feature vector and outputs an image. And then your encoder takes the image and then outputs this token map, right? Or just basically the feature. It is less intuitive to have the same vocab for all resolutions. Yeah, it was a little weird for me too. Like when I read that, I was like, that seems a little weird, right? I would have thought you would have had different code books for the different resolutions, but there's some kind of magic there that I'm not like fully intuiting. And that's totally fine, right? Because I've said this a million times, but like sometimes you can't intuitive these things, right? Like you're really just like a hairless ape that was intended to like hunt megafauna and like live in a small community of like 20 other hairless apes. So, you know, do you really like it? Does it make sense that you should understand like these extremely arcane concepts about like the way that multidimensional tensors and vectors are interacting and like certain things working and not working? So sometimes your human intuition is just not going to be able to grok like why things work this way and not work this way. And you just got to be totally okay with that, right? You got to be okay with not necessarily fully understanding why things work sometimes, but is it because of an extended context across resolution scales? Yeah, I think that it's like the way that I'm intuiting it is because it's like you can have different levels of like the same concept, right? So like there's a vocabulary word that is like a parrot, but then there's also a vocabulary word that's kind of a more finer resolution version of that that's kind of like the beak of a parrot, right? But maybe the beak of a parrot vocab word is, I don't know. I'm trying to like explain this, but I guess I don't really understand why the shared code book is better than having separate code books. Think of it like increasing pixel counts. How do you predict the tokens in R, 4 tokens, all at once based on previous tokens? Or they just predict tokens one by one? No, so the way that you can do that is because you're not depending on the tokens in 2D space, you're depending on the tokens in this kind of hierarchical space, right? So like, if we go back here, in this standard flattened one-dimensional thing, you need token number 5 in order to autoregressively predict token number 6, right? But in this hierarchical space, even though you're still doing autoregression, right, in order to predict this part, you only need these R1, R2, R3. You can predict all parts of this R4 in parallel because this part of the R4 does not depend on this part of the R4. It only depends on this R1, R2, R3. Right? So rather than saying, okay, well, I need to predict this part of the R4 in order to get to this part of the R4, in order for me to predict this part of the R4, you don't need to do that anymore. You can basically say, I can do all of the parts of the R4 in parallel because all of them only depend on R1, R2, R3 rather than other parts of the R4. Yeah, no problem, man. My desire is to help people learn. Okay, implementation details. Would be cool to visually see the codebook, like looking at the layers of an image GAN, a diagonal line token. Yeah, I mean, you could probably do something like that, right? You could take each of the words in the codebook and then like you know, like kind of how people use like saliency maps or this whole idea of like explainability, right? You can like put that vector backwards and then see which things are activating it. And in that way, you can kind of get a little bit of a mechanistic interpretation of what exactly every single little token in this, or every word in this vocabulary represents. But I don't know. I think you're just going to run into the same kind of weird, trippy, like morphy looking things that you get before, where it's like difficult to understand anyways. We use the vanilla VQVA architecture, which I think is a flex, right? You're not doing anything fancy here. You're just kind of using GPT-2 architecture, vanilla VQVAE. Our tokenizer is trained on open images, right? And that's very easy because it's just a self-supervised task because the image is the target. Architecture for standard decoder-only transformers akin to GPT-2. We use the class embedding as the start token. There it is. Okay, so that's start token S at the very beginning here. This one. S is the class token. Normalizing queries and keys to unit vectors. That's also pretty standard. We do not use any of the advanced techniques such as rope, which I never liked rope. You know, I'm just going to be honest with you guys. Like, these rotary position embeddings just, you know, like they sound cool, but then you like dig into it and it's like 700 million different hyperparameters. It's like, you know, I don't like that. You know, I don't like these like hard-coded, like just 20 different hyperparameters all like thrown together into a box, and then you shake it and then you get these magical little position embedding vectors, and somehow that's supposed to be cool, right? I'd much rather have this where you don't need that position embedding, and it just kind of the architecture itself induces the kind of relationship between these tokens that you want, and you don't need to depend on a position embedding to tell you where in the image this token is coming from. Right? Bake it into the actual thing rather than adding this kind of stapling on these rotary position embeddings to achieve the same effect. Okay. So maybe let's go into a little bit of this empirical results, because I want to end with the proof here, because the proof here is one of the cooler parts of the paper. But we're going to get into that later, because here the proof is going to center around this statement here, right? So at the very beginning here, they make a statement where the time complexity of this is O(n) to the fourth, and the time complexity of the kind of raster scan order is O(n) to the sixth. And that's really where this whole idea of the scaling laws comes in, right? So like they're saying, oh, the scaling laws, right? Scaling laws. What do they mean here is that this is more efficient. It's potentially a more efficient and scalable model for image generation than something like a diffusion transformer because of this big O notation proof that they do here, right? Where they basically show that it's O(n) to the fourth compared to O(n) to the sixth. But it starts getting a little bit deep in the weeds, so I'm going to pull us out, and then we're going to look at the results, talk about that for a second, and then we're going to actually bring in, we're going to compare Google AI Studio versus O1 Pro to explain to us those proofs. All right, so here we have the big table. We're comparing against a generative adversarial network here, a GAN, a diffusion model, an autoregressive model that has the standard kind of raster scan, and then we have the visual autoregressive, which is this one here, right? So we can look at the FID scores, 2.3, 2.28, 3.8, 1.73. Inception score, 265, 316, 323, 350, right? So, and then here's the other important part here, time, right? So look at this diffusion model. Look at that, 45 seconds at 7B size. 2B size, 1 second, way lower FID and IS. So these results are good. VAR not only achieves the best FID and IS, but also demonstrates remarkable speed in image generation. Conventional autoregressive models suffer a lot from high computational cost as the number of image tokens is quadratic to the image resolution. A full autoregressive generation of n-squared tokens requires O(n)² decoding iterations and O(n)6 total computations, right? So that n to the 6 is absolutely brutal, right? Because if you patchify this into 9, right, you're now putting a 9 in there and you're squaring that. So the amount of compute is in the order of 9 to the 6 compared to VAR, which only requires log n iterations, and ultimately ends up being big O n to the 4th. So then 9 to the 4th is going to be a much smaller number than 9 to the 6th. Okay. Provides empirical evidence that VAR is about 20 times faster than your vision transformer. Okay. VR is a potentially more efficient and scalable model for image generation. Scaling laws with VAR transformer size n, right? So kind of your standard thing here. Model parameters versus test loss, right? So as you increase the size of the model, the loss goes down. And this is the scaling laws, right? Where fundamentally, what is the scaling law telling you? The scaling law is telling you that, hey, if you trained a model with this many parameters, you can expect it to get this test loss or be this good, right? The test loss, the lower it is, effectively, the more intelligent, the better it is, right? So if that's predictable, then that means that you don't need to be incrementally doing it. You can just design a GPU cluster that'll let you get to here, and then you can expect it to be there. Scaling up autoregressive large language models leads to a predictable decrease in test loss. X can be n, t, c, or c min. N is the number of parameters or the size of the model, the number of training tokens or the size of the data set, and then the optimal training compute, which is how many batches of data are you feeding through here, right? So if you increase any of these, you're generally going to get better performance. If you keep the number of parameters the same, but you increase the data set size, you're going to get a better model. If you keep the number of parameters the same and the data set the same, but train on it for longer, you're going to get a better model. So you have scaling laws with respect to all three of these. Across 12 different sizes. Here's the optimal training compute. You can see it also follows this law here, this red dotted line. And you can see here the different sizes. Pearson coefficients near 0.99 indicate strong linear relationships between log C min, log L, or log C min versus the log error. Test loss, token error rate. These relations hold across 6 orders of magnitude. When trained with sufficient data, larger VAR transformers are more compute efficient because they can reach the same level of performance with less computation, right? So not only is this a simpler concept and a more pleasing and kind of intuitively satisfying concept, right, than this raster scan, but it also is faster and performs better. So pretty much you got to be an idiot to not be using this in 2025 if they're not already using it right now. All right, some limitations in future work here. So we expect advancing the VQVAE tokenizer as another promising way to enhance autoregressive generative models. All right, so there's still a bunch of tricks that they could do to improve the tokenization, right, beyond just this hierarchical multi-scale autoregressive pattern. Text-to-image generation, they're not doing that right now, but they could do that. Currently in our high priority for exploration. And then you can also apply this to 3D, right? So considering multi-scale videos such as 3D pyramids, we can formulate a similar 3D next scale prediction to generate videos via VAR. Compared to diffusion-based generators like Sora, our method has inherent advantages in temporal consistency. So there is the temporal hint, right? So I think one of you guys mentioned this as well, right? Where there's different ways you can take this. You can say, okay, well, now that we've improved the kind of transformer part of consuming an image, can we improve the tokenization part? Okay, there's work to be done there. But now another different thing we can do is work on the applications of this, right? So this paper is just kind of showing it on ImageNet, kind of like a little toy benchmark. So, hey, can we actually now apply this to text-to-image generation, text-to-video generation, image in-painting, image out-painting, like all these different other tasks, see what it looks like, right? And then a third category of future work is what you guys were getting excited about, which is, hey, can you apply this to different types of modalities, other types of data modalities where we're kind of flattening things into one-dimensional sequences in a way that's kind of very unsatisfying? Can we start doing that as well, right? So in the paper, this guy immediately thought of 3D, but some of you guys thought about time. Some of you guys thought about proteins and graphs and different types of data structures that could also benefit from a rethinking of this flattening that we're doing. All right. Why did this win Ben paper? Strong results, promising next steps, well-written, and good figures. This is kind of like... So strong results and promising next steps. I would almost say this is luck, right? So when you think about this guy here, Qiu Tian, he's sitting there, he's doing an internship, he's studying under Li Wei Wang in the Peking University. Li Wei Wang probably gives him a couple ideas, and then Qiu just picks a random idea from that, right? Like, did he pick this idea because he's a 500 IQ genius? Probably not, right? So like a lot of times that if you pick the right idea, I kind of consider that luck, right? So strong results, picking the right idea, and the next steps just kind of follow from the idea. That's almost more luck-based, right? But well-written and good figures, those are skill-based, right? So you can pick an idea and it ends up being a shitty idea. It doesn't work really well, but you can write a really well-written paper and you can have good figures and it'll still be a good paper, right? But in order to win the best paper, you need both. You need both luck and skill. So you need to write a good paper and have good figures with nice little plots and look at this figure's great, but you also kind of need to get lucky, right? And that's the reality of these machine learning conferences now, is they're so competitive that you kind of need to win the luck lottery, and the idea that you pick ends up kind of magically working, right? And like that's kind of what happened here, is that this guy he was like, what if we just do this? And then it just magically, holy shit, that works way better, and it's actually simpler than we were doing before, right? But you couldn't have known that beforehand, right? Like you could have easily tried to do this and it just turns out like shit, and then you're kind of hosed and nobody remembers who this guy is. But that's just the way it works. Jan LeCuck had a stroke looking at this award. I mean, LeCun, I like the Jan LeCuck, but he's I don't know if he's the one. Like he was definitely there in the very early days of convolutional neural nets. I don't think he's like the original convolutional neural net guy, but like he has understood this kind of prior his entire life, right? Like Jan LeCun is very aware of this kind of prior of like, okay, you have different resolutions and this hierarchy of resolutions, and you have this like spatial kind of relationship where at the lower resolutions you have a little bit larger of a receptive field corresponds to like a smaller receptive field in the higher resolutions. Like he understands that very deeply. So to him, someone coming out and basically creating just recreating that or re-deriving that exact same prior in a slightly different clever, like to him it probably feels like a very simple idea, right? So he's probably just pissed that one of his students didn't actually do this and get good results, because like all of his papers have this prior in there already, right? It's like everyone in the computer vision space thinks like this multi-scale resolution stuff. Like it's just that this guy managed to put it all correctly in the right little order of things. Text generation examples. It would be interesting. Okay, I think you guys might be talking about something else. Maybe LeCun is right about this LLM is not the end of the road idea. What does end of the road mean? I think that the transformer architecture and language models, like everything that we're doing now is more than enough to take us to AGI and ASI, right? Like I was playing with this demo. Actually, this is a good introduction here, right? Like playing with this demo, which is literally free, like this is going to change the entire world, right? Like this is more than enough to materially impact every single market, every single country, like every single person. The way that you're interacting with computers is going to fundamentally change. You don't need like a new innovation in model architecture space or in like just deep learning in general in order to get to radical transformations in our world. I think we're already there. So I feel like to me, Jan LeCun is a little bit like he thinks that you need to get another like 100x like improvement in order to see like changes. But to me, it's like the changes are going to happen regardless. What we have right now is more than enough to get to the point where the world is completely changed, right? And the important thing to realize there is that at some point, the human is no longer going to be driving progress forward, right? So this idea that Jan has that we're missing a couple missing pieces, right? Like the humans aren't even going to discover those missing pieces. An LLM is going to discover the missing piece. And how unsatisfying is it going to be for Jan LeCun when an LLM like fucking O1 Pro running in some kind of agent loop discovers something like this, which ends up giving us ASI, but we don't even care because we're all too busy just playing video games inside these like VR metaverses. I don't know if that made sense, but... Is a mosquito ASI or AGI? I think it's neither. It's conscious. It's not solving, like, how many problems do you need to solve before you're considered general? Right? AGI is artificial general intelligence, and the keyword there is generality, which is basically like how many different tasks you can do. Artificial superintelligence means that you're super intelligent, which means you're better, you're extremely strong. But you can be ASI, but not AGI, right? So if you think about the DeepMind Go playing AI, that is super intelligent in that it's better than any human at Go, but it's not a general intelligence because if you couldn't even ask it, like, are Smurfs blue? You know, like just a random, like, is the Eiffel Tower in Paris? Like, you can't even like formulate that question to the Go playing AI. So to me, AGI already happened. AGI was ChatGPT, right? The fact that you could ask ChatGPT like a medical question and then you could ask it to make a poem and then you could ask it to like, you know, like that is more than enough different types of tasks that to me that fulfills the definition of generality, right? But I think what people are really expecting is something like a super intelligence that also is general. And I think we're getting very close to that, right? Like something like this, like the O1 Pro mode, it's both general and super intelligent, right? Like how many people are better at math than this O1 Pro? Probably like 1% of all humans, right? How many people are better at chemistry than O1 Pro? Probably less than 1%. How many people are better at poetry than O1 Pro? Probably less than 1%. So like you're starting to get to the point where it's surpassing humans in pretty much every single task that humans can do. And I think that's kind of what people are defining as AGI. But I think if you want to be very specific, to me, AGI was reached with ChatGPT. Yeah, push the goalpost until it beats humans in everything. Yeah, exactly. Mosquitoes can make mosquitoes. Can you make a mosquito? Can you make a mosquito? Let's see. Let's see how long it thinks about that. How to make a mosquito. All right. All right. Let's go here, though, because I thought this was pretty cool. So this is the proof. At the very bottom of the paper, right, they're basically saying, oh, actually, wait up. Let's look at this. Token dependency plotted the normalized heat map of attention scores in the last self-attention layer of the VQ-GAN encoder. So this is what it's paying attention to. It drew an ASCII art mosquito. But going back to here, I thought this was kind of cool because it's showing you like, you see initially, right, at this layer here, it's really not paying attention to this at all, right? It has this very kind of localized, somehow diagonal. I don't know why that necessarily turns out that way, but you can see how it's like, it's paying attention here, but not here. And then kind of as you go higher up, it starts paying attention to the whole thing. So this is very reminiscent of kind of even just within a ConvNet, right? Where like, as you go up in these hierarchies, each individual layer there and the neurons within those layers are representing concepts that are kind of have a receptive field of the entire image, right? Especially once you get to the top, those little neurons at the top are representing effectively every part of the image, but at a higher kind of semantic level, versus once you go to the lower layers, you're representing more kind of spatially restricted concepts that are just in this little corner over here, or like just this top part here, and so on. All right. Not going to lie, I think we are 1,000 innovations away from AGI. I don't know about that. Okay. Let's do this. You guys should definitely try this. aistudio.com.google or aistudio.google.com/live. And then you go here and you hit stream real time. And then you do share your screen. And then let's open up this one here. And I'm going to turn on the application audio capture so you guys might hear my voice twice. Your screen. And then let's open up this one. Hey, can you help me understand this time complexity proof? I'm going to turn on the explain the concept so you guys computational complexity, time complexity, and your screen. And then let's open up this one. Hey, can you help me understand this time complexity proof? I'm going to turn on the explain the concept so you guys computational complexity, time complexity, and your screen. And then let's open up this one. Hey, can you help me understand this time complexity proof? I'm going to turn on the explain the Okay, sorry about that, guys. Let's try that again. It's hard refresh. Share my screen. This. Help me understand equation number 17 in this proof for the time complexity of autoregressive generation. Wow. Let's try that again. Can you help me understand this proof? All right, guys, I don't know what I did. I pissed it off or something. Hello? Why is it ignoring me now? All right, we'll try one more time. If it doesn't work, then fuck it. Jesus Christ, Google. Come on, Google. I was literally about to talk about how cool it was, and then you're here just looking like shit. Hey, I'm trying to explain this proof. Can you help me?
Sure, I can help with that. Please tell me what you need help with regarding the proof.
Help me understand the difference between time complexity and memory complexity. Something went wrong. All right, guys. Either way, maybe it's just because I'm streaming or something. Like I don't know what could be going on. Maybe it's because I just keep refreshing, and at some point they think I'm like a bot that refreshed this page like 4 times or something like that. But it was working pretty well, and it was kind of getting some of this. But I guess we can go to here. Attention complexity explained. So I took screenshots, and I gave it to ChatGPT o1 Pro mode. And this was also pretty good too. Like, we're starting to get to the point where like these are really clean and almost better intuitions, right? So in short, ON of 6 does not come from changing the fundamental OL squared, right? This is what you usually see in any kind of transformer, kind of Mamba paper, any kind of like paper where they talk shit on transformers because of this L squared attention complexity. It comes from applying that quadratic complexity at n squared successive autoregressive steps, each step having a gradually increasing sequence length up to n squared tokens, right? So where this O to the 6 is coming from is that at the first token, there's no previous concept, so the complexity is negligible. So this very first token here, right, if you're doing this flat raster scan kind of order, the complexity of the first token is just O of 1 because that's the attention is between only this token. And then once you get to the second one, now you have to do an attention map between 1 and 1, 1 and 2, 2 and 2, and 1 and 2 and 2, right? So like the whole square. So that's O of 2 squared. Once you get to 3, it's O of 3 squared, and so on, all the way to the nth token, which ends up being O of I squared. So if you sum all of those together, right? So you're summing those from token I all the way to n squared because there's n squared tokens here, right? Where n is effectively just the size of the image, right? So just to make things simple, when you're doing these type of complexity calculations, you're rounding everything out, right? You're kind of saying, okay, well, rather than saying, hey, usually the width is a little bit bigger than the height, let's just say the width and the height are the same, and we have just this number n that defines the size of the image. So, or effectively the number of pixels in there. If you sum all of those up, you can actually use this sum of squares formula to turn this summation here into this expression here. And then if you expand that all out, the dominant term there is n to the 6. Okay, that makes sense. For VAR, we first need to define this resolution sequence. This is the hyperparameters that I'm talking about, right? But this is like 500 IQ here. They define this rather than saying, okay, there's going to be some H and W for the first resolution and some HW for the second resolution and some HW for the third resolution. They're going to formulate this. They're going to basically create this hyperparameter A, which allows you to get each of these for all of the resolutions. So they reduce what is normally like 12 different hyperparameters into this one meta hyperparameter from which you can derive these other hyperparameters. And then they plug that in here, right? This is the same I squared, n squared. Oh, this goes up to K because you have the K resolution maps rather than the n squared total number of tokens. And then look at this shit. Here. Problem of considering a sequence of solutions, you have this geometric progression. So by formulating this hyperparameter in this specific way, right, you now have this geometric progression, which means you can get this formulation here and then get this right there and then get it right there. So like, I'm not like a super math guy, you know, like I would say I'm like a level 1 math guy. This guy is definitely like a level 4 math guy, level 5 math guy. Because like the jump from, okay, this is really this, okay, but jumping from the many hyperparameters to this, and then jumping from this to this, like, you got to know that. You got to like look at that and be like, oh yeah, that obviously that is that, and obviously this is this, and obviously this is this, which is kind of, you know, the sum of a geometric series with the first term T, R, and K is this, right? Like, damn, dude, like, how did he know that off the top of his head? All right, sum up all the autoregressive generations, you put all of these things together, and the dominant term here is this n to the 4th. So O n to the 4th for VAR, O n to the 6th for standard autoregressive with the raster scan pattern. And that's why it's 20 times faster. Too complex. Should we try it? Let's try it again. Maybe let's see if we got it. Maybe we just needed to pause for a second. Stream real time. Hard refresh. Share your screen. Can you help me understand how to go from this step that I'm highlighting into this step that I'm highlighting?
Sure, let me help you with that. The step you are highlighting before equation 19 sums the series using a formula for a geometric series, then the result of that sum is plugged into equation 19. Do you have other questions about it?
How can you make a mosquito? Can you make a mosquito?
I can't create a mosquito, since I am only a language model. Is there something else I can help with?
All right. That's it, guys. That's what we got. The mosquito benchmark, dude. But the key part about the mosquito benchmark is you got to hit them when they don't realize it, right? So you gotta wait, and you gotta make them do something else, and then you hit them with the "Can you make a mosquito?" It needs some work. Kind of boring answer. Yeah, it wasn't as cool in hindsight. I thought it was gonna be pretty cool when I was like planning for this stream. I was like, oh, it's gonna be so fucking cool. I'm gonna be doing this, and it's gonna like show you the proof, and then kind of ended up not being as cool. But either way, that was basically the paper, guys. Visual autoregressive modeling. It won the best paper award at NeurIPS. There was the weirdness here that I don't really fully understand. Like, he somehow poisoned the model. Like, what the fuck was this a mistake? Was he just like kind of like a junior engineer and he just like accidentally deleted a file? Or is it like he like purposefully went in there and like, you know, like obfuscated or changed something weird? Like, I don't know. I don't know what the actual story is. I don't have any cool insider stuff there, but the paper was pretty cool. You know, I think it was well written. I really liked the sections here. Like, they're very clean. You know, he really like kind of makes the case why this is a better prior to use than this kind of classic raster scan ordering that we do now. I think that this idea of multi-scale, like multi-resolution, is something that goes all the way back to ConvNets, and that goes all the way back to kind of some of the original analyses of like the way that neurons in your brain are organized. And I think I'm very pleasantly surprised that they get a really good scores here on these benchmarks. So that is like simpler intuitively, and not only is it simpler intuitively, but it also is faster just inherently. Like the time complexity, the computation complexity is O to the 4 instead of O to the 6. So yeah, I think we're probably going to see this in any kind of image generation, any kind of vision language model, any kind of even video models. And then we're probably going to see similar papers for different types of data modalities like 3D and potentially even some of these kind of more niche modalities like proteins and graphs or other weird types of data structures like that. But that's basically the paper, guys. Why language models are great at some hard problems, but then they fail simple arithmetic? How would you explain this without saying it's just simple pattern matching? The model is returning the tokens that have the best likelihood, right? Like fundamentally what you're doing here is like you're picking the next token based on this kind of like statistical kind of Bayesian modeling of like, okay, well, if I have millions and millions of tokens, like what's the next token that came up here based on my data set? So why is a language model bad at some like 1 + 1 = 2 type of question, but then it can answer these extremely complicated questions like this, right? Well, part of that is because the intuition that you have around what is a hard problem and what is an easy problem is not correct, right? It's based on the way that your brain works, but LLMs and these type of deep learning models, they work fundamentally differently. So something like 1 + 1 = 2, like that probably comes up millions of times in the training corpus, and there's like potentially wrong versions of that and different wordings of it. So like picking the right token in that sense is probably more difficult than picking the right token for something like this, where it's like, this is a very narrow part of the training distribution. So it's almost like it's more certain. I don't know. I'm not necessarily in love with that explanation I just gave, but I think the core intuition here is that you can't assume that things that are easy for humans and hard for humans are also easy for LLMs and hard for LLMs. It's like they're operating under a different type of world. So things that are easy for them might be hard for you, and things that are hard for you might be easy for them. Can we get intuition from super resolution POV of formulation? Like super resolution is all you need for image generation? I mean, it's not all you need because you're still using all the different tricks, right? So like this type of next scale prediction is just one piece of it, right? Like they're still using a transformer, which means they still have little multi-layer perceptrons in there. They still have attention maps in there. You know, you're still using this VQVAE in order to do the actual tokenization. So there's still a lot of pieces there, right? It's not like they deleted everything and only used this multi-scale thing. It's like that's just one piece of it. How much performance improvement does this produce for Gaussian splatting? This is like orthogonal to Gaussian splatting, right? Gaussian splatting isn't like feeding stuff into a transformer. There are Gaussian splat papers where you're generating a splat potentially autoregressively, and in order to do that, you're maybe flattening out what is a three-dimensional collection of splats into kind of this one-dimensional sequence. And maybe when you're doing that, there's some way to rethink that and be like, okay, rather than kind of rastering through my volume of space where my Gaussian splats are defined and then coming up with this random ordering that's just left to down, top to right type of thing, maybe there's some ideas here that you could do that, but this isn't going to immediately be applicable to Gaussian splats because they're different enough that it's like you're dealing with different problems. Could we use this for rendering a splat? You're already kind of doing that, right? Splats are rendered in tiles, right? So here's the fundamental way to think about Gaussian splats is that it's a set of splats, right? It's an unordered, like they're not ordered, right? You're basically saying here's a splat and then they have this position in space, and then here's a bucket of like 100,000 splats. But when you're consuming those, in order to create those splats, you're pushing gradients directly into the position of the splat. There's no sense of like this raster scan ordering in the splats. Do you think synthetic datasets that have step-by-step thinking would be great for training an LLM? They're already doing that. O1, these type of models like this, the O1 Pro mode, these type of reasoning models, they're trained with synthetic data that gives you a correct reasoning tray. So they basically, one way to think about how these type of reasoning models are trained is that they take something like math or code where you know what the final answer is, then they take a model and they have it create a chain of thought and then get to a final answer. And then they take the ones where the final answer is correct, and those are examples where you're like, okay, this chain of thought got you to the right answer, and then this other chain of thought over here got you to the wrong answer. So now I'm going to push a gradient into the actual model that is saying this chain of thought is good, this chain of thought is bad, right? That's obviously an oversimplification, but you are pushing gradients into these reasoning models from data sets that are synthetically created by models. Right, so it's like the data that's going into O1 Pro is not just internet data. It's like outputted by another LLM and then refined. Can we get intuition? I think you already asked that. Thanks for the great streams. I appreciate it. If we stop our research today, we need 10 to 20 years to implement current AI things at prod. Yeah, I agree with that. I think that there's a lot. Kind of, this is the point I was trying to make earlier in the stream. It's like, I feel like we've already gotten more than enough. Like, we have more than enough right now in terms of new technology to drastically change our world. Like, even if we like killed every single AI researcher right now, like we would have more than enough to basically transform everything. The way we interact with computers, like every single job is going to be different. So I don't think we need any more innovations, but the innovations will just further accelerate this singularity. Let's do this. Gaussian splat generation transformer. I'm going to see if I can find a paper where they use raster scan for the splat. Point transformers, text to 3D using Gaussian splatting. GS Gen. Point transformer, let's see if this one has it. Okay. If we do this and we control search in here. Yeah. Real-time rendering with rasterization-based tools. That's not what I'm looking for. We feed the model, rasterize the predicted Gaussian primitives to the OOD test views. Yeah, so I think if you're looking for how this paper impacts Gaussians, it's like try to find a paper where they're feeding Gaussians into some transformer such that it either generates another Gaussian splat or some kind of like text to Gaussian or anything where you have a transformer, right? And I bet you that when you actually put it into the transformer, right here, this point transformer encoder, it's probably getting flattened. And as soon as you have a flattening, that's where you can do this type of shit. So anywhere where you have some kind of high dimensional data modality that gets flattened into a one-dimensional sequence so you can put it through a transformer, that's where you can take the learnings from this paper. Slam GS papers. Yeah, there's a couple different Slam GS papers. 15 minutes and an OpenAI will have the show? Okay. All right, is that the next OpenAI's coming out? Apparently they're releasing some hot shit, but we'll see. Google kind of, pulled out a pretty good, strong showing with the Gemini 2, so I don't know. We'll see what we get. All right, guys, I'm pretty much done there. I need to go do some stuff, like watch that OpenAI stream. But thanks for watching, guys. Thanks, OpenRoom XYZ, Spirabel, Longtran, Mind of a Tool, Sarah, Sheb. Who else? Atashe, Jike Z, A Skeletal Ghost. Keep scrolling. A lot of the same people talking here. Jike Z, ZZZZZ, Aries, Chicken P, Majetti, NLP, Patrick, Sarah, Andre, Ton Bin, Isaac, Saskia. Thanks for hanging out. Hope I helped in some way. If not, I apologize. See you guys next week. And thanks for hanging out.